Hi everyone, I am Hardik Soni from Cornell University. In this video, I am going to talk about composing Dataplane programs with mP4. This work is done in collaboration with Miriana at Nokia, Praveen, Ryan, and Ned at Cornell University. Over the past decade, the way we build and manage networks has greatly transformed. We are moving towards complete softwareization of networks. And what do I mean by softwareization of network? Well, software is running in network devices increasingly look like any other software running in operating system, database, or compute machines. And this transformation has happened thanks to emergence of software-defined networking, packet processing languages like P4, and domain-specific hardware. But networks are still quite different, at least in the case of Dataplane. To develop Dataplane software, we are still writing code at very low level. We are writing code at pretty much machine level or assembly level. Also, we lack the ability to develop Dataplane software in a modular way. This is a very sorry state of Dataplane programming. Because, according to MIT professor Barbara Liskov, modularity is one of the key principles in software design, if not the most important principle. She has put it in her 2008 Turing Award speech. Modularity based on abstraction is the way things are done. Why is modularity so important? Well, a modular approach to develop a large system would be first decompose the system into small pieces that can be developed independently so that we can design, develop, and test these small pieces efficiently with high quality. Also, once we have these small pieces, we can identify common code fragments that can be used across different systems so that we can develop a library of these common code fragments and reuse to make different new systems. Now the question comes, how do we build reusable libraries? Well, for that, we write a library code in a higher level language or with a higher level abstraction. And then we use a compiler to port this library code to different target architectures or devices. So now that we understood how we can develop a large system using a modular approach, let's have a look at what is the current situation in case of Dataplane software. We are going to look at a widely used and open source switch software. The switch software is maintained by P4 language consortium and it implements variety of features. Namely, it implements L2 multicast, L3 multicast, routing, ECMP, etc. So let's look at how these different features are implemented. Here I'm showing you a small code snippet of code base. The concerned fragment here is related to IPv6. As you can see, the logic is guarded using a C-style preprocessor. And not only for small piece of code, but the entire software is guarded with various preprocessors for different features. And from our past experience of software development, we know that how difficult it is to maintain a code that uses huge amount of preprocessor. And because for every different feature, a preprocessor is used, the whole software is made using a spaghetti-like code. So what is the scenario here? The situation is in one of the most critical part of network, we are writing spaghetti code with C processor strings wrangle around. And that too, we cannot maintain or extend such code base. So can we do better? Wouldn't it be nice if we can have a small pieces of code and put them together to create a switch-like software that can be executed in a Dataplane? Next, we look at what are the key challenges we face in implementing switch software in a modular way. So we are going to look at 3 key challenges posed by P4. P4 programs are monolithic. Second, P4 programs are written for heterogeneous programming model. And third, P4 programs are tightly coupled to target architecture. So let's look at the first challenge. Why P4 programs are monolithic? Consider if we want to implement IPv4, IPv6 or MPLS routing. So what is the current situation with P4 to develop such a data plane packet processing protocol? Here I am showing a code snippet from switch.p4. And as you can see, there is something called L3 retype. And in this, IPv6 disable preprocessor used, and that is used to guard IPv6 related code. For example, at line 197. And similarly, for other different protocols, different preprocessors are used. For example, MPLS, and then for IPv4, etc. So if a programmer wants to modify feature of any of the protocols, what they have to do is to go around in the code and find out what is the preprocessor associated with particular feature and modify code for every place the preprocessor used. So this code is not maintainable, and also it is really hard to reuse such code. That's why the P4 programs are really monolithic. The next challenge, P4 has a heterogeneous programming model. So P4 provides two sub-languages for packet processing. One is state machine based packet parser, and second, match and action based packet processing. In addition, P4 provides something called extends, and these extends are used to program fixed function exposed by target devices. Now let's look at why this heterogeneous model is a challenge. Well, consider a scenario where we have a caller program, and that invokes a callee program. For example, if a caller program invokes callee after finishing its match and action based packet processing, then a callee may start its execution from parser, which has a state machine based model. So program control needs to be transferred from match and action based packet processing to state machine based packet parsing. And we know that both of these have a different abstract machine and different model. So it is not possible to transfer program control between two incompatible programming models. And this makes composition of P4 program a challenge. Next, P4 programs are tightly coupled to target architecture. Here I am showing example of portable switch architecture. It has ingress programmable block, fixed function packet buffer, and egress programmable block. A typical P4 program for PSA would have to implement all the programmable blocks. Here, for example, I am showing cartoon picture of ingress programmable block. Now consider a P4 program written for PSA required to be deployed or execute on something like Spectrum Mellanox switch, which has a completely different set of programmable blocks and different pipeline layout here. It is not evident how we can map down ingress of PSA to flex 2 or flex 3 of Mellanox. Therefore, code fragment written in P4 for a specific architecture cannot be reused on another architecture. It is really difficult to port P4 programs across different architectures. To address these three challenges and enable modular approach for dataplane programming, let me introduce to our solution micro P4. And first I explain the key design insight that led us to micro P4. Higher level abstraction for dataplane. Because we want to develop dataplane code that can be used against different target architecture, we need to have a higher level abstraction for dataplane, so that different dataplane software code can be written against this higher level abstraction, and then we can have a compiler that maps down this higher level abstraction to target specific architectures. Second, we need to homogenize the programming model, because P4 provides different sub-languages and makes composition of P4 programs really difficult. We need to homogenize not only packet parsing or match and action based packet processing, but entire packet processing model in a more general way. With these two key design insight, we are going to look at micro P4. The first component of microP4 is its abstract data plane model. The model is very simple. It provides logical pipeline and logical buffer. The idea is programmer can write microP4 module using simple parser, control, and deparser, and then a microP4 would read a packet from a buffer, process it, and write. The idea is to distill packet processing down to its essence as a three-stage read, process, and write function. Here, input and outputs are logical buffer, and they provide common interface for composition. So now let's look at what does data plane model of microP4 abstract away. First, pipelines. P4 provides architecture-specific pipeline, whereas microP4 provides logical micro-pipeline. P4 provides architecture-specific metadata for packet processing. For example, to drop a packet or to replicate it. microP4 abstract away this information by providing logical buffer. P4 targets exposes fixed function, whereas microP4 provides logical extents that can be mapped down to different target-specific extents. On the right side, I'm showing you the design of microP4 module, which contains very essential element for packet processing, where on the left side, the data plane model of PSA is shown. And as you can see, it exposes various details, for example, ingress, egress, fixed function, packet buffer, etc. So now that we understood what sort of or what kind of abstraction microP4 provides, let's look at how does it provide composition. Here I'm showing two microP4 modules, and to enable sequential composition, what we have to do is essentially attach output buffer of first module to input buffer of the second, and this way we can have a sequential composition. And now if you look at carefully, this microP4 composed entity can be again considered as a microP4 module by associating input and output buffer to it. The another key component of microP4 is its compiler. Because microP4 provides abstraction for entire data plane model and pipeline, it hides huge amount of complexity which was earlier exposed to programmer by target specific architectures. So in that sense, microP4 compiler is very different than target specific architecture because it hides a huge amount of complexity to provide a nice abstraction. Essentially, microP4 compiler is source-to-source compiler. microP4, the compiler takes program return using microP4's logical pipeline and translate that logical pipeline-based program to target-specific P4 source code. We have implemented microP4 compiler using open source P4C framework. We added 14,000 line of code, which was written in C++, and to provide portability, we have two backend. One is software switch based, and that is BMV2. And another backend is for hardware target, Tofino. The approach for our compiler is to homogenize source program so that we can have various analysis, transformations, and composition done. Then we rearrange the code to respect target specific constraint. And the idea here is to translate logical pipeline to target specific pipeline. And finally, emit the code for target specific packet processing blocks exposed by the architecture. So let's have a deep dive into compiler. The compiler has three key passes: front end, mid end, and back end. Compiler takes microP4 program written against its logical pipeline as an input and translate and generate target specific P4 source code. We are going to focus on two key passes. One is in mid end and one is in back end. The mid end pass, which is a key for us, is transformation to match and action control block. It takes logical pipelines, which has a parser, controller, and deparser, and homogenize all the programmable blocks of logical pipeline to control blocks. And the second key pass, which is in the backend, is to translate this homogenized micro P4 IR to target specific P4 source code. First, homogenizing abstract machine. Programmable parser are state machine based. Every state in the parser performs certain operations. One typical operation is copying bytes from packet stream to header phase, then match particular value with byte extracted bytes, and then transit to another state. So if we think carefully, these operations can be considered as a match and action, where match is on bytes and in the packet, and action is copy or extract bytes and transit to another state. So essentially, parser performs repeated match and action. So we can say that we can transform a programmable parser into match and action based packet processing. Now the question is, how can we know, or how many bytes need to be extracted, or how many bytes needs to be have access to before we can perform such match and action based packet processing and emulate parser inside the pipeline? Well, for that, micro P4 performs certain static analysis, and the detail for the analysis is given in the paper. We move on to the next pass, that is the key pass in the backend. Backend operates on homogenized micro P4 IR. In this example, I am taking target architecture as a PS architecture. It has a ingress programmable blocks, fixed function packet buffer, and egress programmable blocks. So target architectures usually expose some constraint. For example, one such constraint, I give an example here, is that in PSA, in egress programmable block, you cannot write on output port. That means forwarding decision has to be decided in ingress. So micro P4 takes into consideration such constraint. In this particular example, it partitions micro P4 IR into ingress and egress. Then it transforms and synthesizes required packet processing block. Look at how do micro P4's abstract data plane model and compiler perform in practice. And for that, we ask three simple questions. How expressive is micro P4's buffer-based composition model? How can we develop common set of functions as a library and perform various composition? The second question we ask is, can we run the same program on different target architectures like BMV2 and Tofino? And third question we ask is, compared to monolithic program, what is the resource utilization of micro P4 compose program on hardware architecture like Tofino? So we answered this question one by one. To assess the expressiveness of micro P4's data plane model, we develop set of micro P4 modules. Namely, we develop IPv4, IPv6, routing protocols, network address translation, etc. And as you can see, each module contains few hundred lines of code. We composed these micro P4 modules in many different ways. And for that, we generated 7 different programs, which essentially includes different features. And these features are micro P4 modules. And we did a case study on a modular router. For example, we took a P3 program, which involves a variety of routing protocols, namely IPv4, IPv6, and segment routing 6. Then we run the same micro P4 program on BMV2 and Tofino architecture to understand what sort of challenges we face when we implement different backend for target architecture to achieve portability. We run a micro P4 generated source code on a barefoot Tofino architecture. Here, idea is to assess the resource utilization and overhead due to various transformation performed by micro P4. Hardware target architecture like Tofino has 2 main resources. One is parse header vector, and another is match and action unit in its pipeline. Here we are showing utilization of match and action units. As you can see, micro P4 compose program consumes a lot more match and action stages compared to its monolithic counterpart. For example, for P3, micro P4 compose program takes 8 match and action stages compared to 3, which is consumed by its monolithic counterpart. We encountered 2 critical scenarios. One is there are micro P4 compose programs which could not compile to Tofino architecture due to resource constraint. And we also encountered a scenario where a P4 monolithic program specific to target architecture, which is a Tofino, could not compile to Tofino architecture using barefoot compiler, whereas micro P4 compose program implementing the same set of features could compile to Tofino architecture. In the end, we say that micro P4 is our ongoing work. We acknowledge that micro P4 does not implement all features. Our ambition and our goal is to have all the features of current P4 spec to be implemented in micro P4. Our design supports packet replication and multicast, but micro P4 compiler does not implement them. In addition, we plan to implement variable length headers, stateful packet processing, contour plane APIs, etc. Our goal is to transform micro P4 into LLVM-like system for Dataplane programming. Finally, SIGCOMM was right. Modularity based on abstraction is how things are done, and micro P4 does that. Micro P4 implements language design. It implements higher level abstraction for Dataplane programming. It provides compiler that composes different modules into a single program, and then it generates a code to translate this abstraction into target architecture specific Dataplane model. We develop an experience in creating a modular router. Finally, I would like to conclude saying that micro P4 enables portable, modular, and composable Dataplane programming. Thank you for your time and attention.